Okay, so we're going to be finishing up chapter 15 today with the discussion of reaction quotient and then discussing how to determine the concentrations of each substance in a reaction at equilibrium. Now, folks, reaction quotient is related to the equilibrium constant. Their expressions are derived the exact same way. The difference between a reaction quotient and an equilibrium constant is, if you are calculating the equilibrium constant, then you are determining the value at equilibrium, meaning the reaction has ceased to progress left or right. It is the rate of the forward reaction and the rate of the reverse reaction are identical. If you're calculating the reaction quotient, Q, the reaction quotient tells you the direction the reaction is going to shift in order to reach equilibrium. If your Q is less than the K value for the reaction, it is telling you that the reaction has to shift in the forward direction, meaning it has to go from reactants to products in order to establish equilibrium. If your Q value is equal to K, that means you are at equilibrium. Finally, if your Q value is greater than K, it means that the reaction has to shift back towards the reactants in order to reestablish equilibrium. So again, the difference between K and Q, K means it's at equilibrium. Q means that there's a question mark as to whether it's at equilibrium, and it describes which direction the reaction is going to proceed. Otherwise, you're calculating Q and K the exact same way. You're developing their expressions the exact same way. Meaning it is the product, the multiplication of the products raised to their coefficient, divided by the multiplication of the reactants raised to their coefficient. Just like with K, Q only includes aqueous compounds and gases, because just like K, those are going to be the only two states of matter that we see dramatic enough changes in order for it to really impact the equilibrium constant. Question. What we're going to do now is we're going to look at a couple of examples, and we're going to, I believe, and we're going to predict the direction that the reaction is going to proceed. By the way, because I'm trying to let some folks that are writing catch up to me, where have you heard that a reaction has to proceed towards the reactants or to the products in order to establish equilibrium? We discussed it with Le Chatelier's. The reaction is not necessarily at equilibrium in Le Chatelier's. It's going to proceed to the left or to the right to reestablish equilibrium, meaning that you can use the reaction quotient to calculate where you are in the equilibrium process, and it would predict whether you're going to go towards the reactants or towards the products. So the equilibrium constant can be used with Le Chatelier's principle. So let's look at an example. Consider the reaction where ammonium hydrogen sulfide goes to form ammonia and hydrogen sulfide. The Kc for this expression is 8.5 times 10 to the minus 3. Your reaction mixture in the laboratory contains solid ammonium hydrogen sulfide. It contains 0.0822 molar of ammonia and 0.0822 molar of hydrogen sulfide. Will more of the solid form, or will some of the existing solid decompose as equilibrium is reached? Okay, so basically we're at the question, the Q, of whether it's at equilibrium or not. Q's expression is developed the same way as K's expression, meaning it is the products raised to their coefficient divided by the reactants, which we only include aqueuses and gases, and therefore it is over 1. So we can calculate Q. Q is going to be equal to 0.0822 for the ammonia and 0.0822 for the hydrogen sulfide. Meaning that the Q value is 0.00676, or to get it in the same format, it would be 6.76 times 10 to the minus 3. Now we're going to compare Q and K. Is Q greater than, equal to, or less than the equilibrium constant? Q is less than K. Since Q is less than K, it means that the reaction proceeds in the forward direction to make more product. Therefore, solid is going to dissolve or dissociate as a result of this reaction. So the existing solid decomposes. Questions? If you don't like looking at numbers in scientific notation and comparing numbers in scientific notation, you could have taken both of them out of scientific notation, and that may help you to better see that the K was larger than Q. Let's look at another example. Silver sulfate dissolves in water according to the reaction where silver sulfate solid dissociates to form 2 silver ion and sulfate ion. The Kc for this is 1.1 times 10 to the minus 5 at 298 Kelvin. A 1.5 liter solution contains 5.14 grams of dissolved silver sulfate. If additional solid is added to the solution, will it dissolve? Okay, so basically what we have, the first thing we have to do is when we're talking about K or Q, we develop the expression. In this case, it's going to be Ag2 plus squared times SO4 2 minus over 1, because we don't include, I should say we only include aqueouses and gases. The brackets mean concentration. So one of the first things I have to do is I have to get the molarity of the silver sulfate that has dissolved. So the molarity of the silver sulfate, first thing is let's get the grams into moles. 5.14 grams of silver sulfate for every 1 mole of silver sulfate. Talking about a molar mass of 203.86 grams per mole. So we're talking about 0.0252 moles of silver sulfate. We then get the molarity, that 0.0252 moles of silver sulfate is dissolved in 1.5 liters of solution. So we're talking about a concentration of 0.0168 molar silver sulfate. Now, here is one of the first lessons that's going to go into what we're going to discuss in the next part of today. We're going to take this silver sulfate equation and we're going to look at this. So what we know is that 0.168 molar of silver sulfate dissolved. According to this equation, for every 1 Ag2SO4, you get 2 Ags. So in other words, the concentration for the silver is 0.0336, and the concentration for the sulfate is 0.0168, because it's in a 1-to-1 ratio. So these are the concentrations we're going to plug into our Q expression. So Q is equal to the silver squared, so 0.0336 squared times the sulfate of 0.0168. And you get a value for Q equal to 1.9 times 10 to the minus 5. Now, the question is, what is the relationship of K and Q? Is 1.9 times 10 to the minus 5, which is Q, greater than, equal to, or less than the Kc of 1.1 times 10 to the minus 5? It's greater than. So Q is greater than K. So that means that the reaction proceeds towards the reactants. So in answer to the question, no, the additional solid will not dissolve. Questions? We're going to use several of these concepts that I just illustrated in this problem, not only when we're talking about using a balanced chemical equation to figure out concentrations, but also later on when we get into the solubility product equilibrium constant. Folks, while I'm on this slide, a side note. If you use your solubility rules, the rule for sulfates is that sulfates are soluble except for lead 2 plus, silver plus, mercury 2 plus, barium, strontium, and calcium sulfate. So according to your solubility rules, silver sulfate is insoluble. But what does that actually mean? Why do we say it's insoluble? By having an equilibrium constant, it would suggest that some does dissolve. The fact is, in College Chemistry 1, when we talked about the solubility rule, we were describing essentially the equilibrium constant. Because if you think about the last exam, we said anything that had an equilibrium constant less than 0.001 is almost entirely reactant. This is less than 0.001. So it's almost entirely reactant. So so the point I'm trying to get at is your solubility rules indicate how soluble something really is. If it said it was insoluble, it meant that it had a fairly small equilibrium constant. If it says it's soluble, it means it's going to have a fairly large equilibrium constant. So that's how your solubility rules came to be. Questions? Now, one thing we really haven't talked about, or maybe I brought it up, in fact, I know I brought it up, is you are going to encounter different equilibrium constants. The one that we have focused on most of our attention on has been Kc. Kc, the C stands for concentration. So in other words, we're talking about molarity. We're talking about the molarity of the reactants, the molarity of the products. Another one that is possible is Kp, and Kp stands for pressure. So in other words, we're talking mostly about gases here because they're the ones that apply the pressure. And so that's why you're going to see this discussed in terms of atmospheres rather than concentration, is because we're talking about pressures of gases. Some other ones that we will encounter include Ka, which we're going to start that either late this afternoon, today or Thursday, and that means it's an acid. Kb, the B stands for base. Kw, the W stands for water. KSP, SP stands for solubility product. So in other words, this is what I was just talking about with respect to solids that are only partially soluble. So these are just different, they're still Ks, meaning they're still equilibrium constants. So you're still going to develop this expression the exact same way you've been developing the equilibrium expression. They're just using slightly different units in the case of Kp compared to Kc, or they're describing a specific type of substance in the case of Ka, Kb, Kw, and Ksp. So in this case, consider the reaction where hydrogen sulfide reacts to form hydrogen and sulfur. A reaction mixture contains 0.041 atmospheres of hydrogen, 0.037 atmospheres of sulfur, and 0.615 atmospheres of hydrogen sulfide. Is the reaction mixture at equilibrium? If not, in what direction will the reaction proceed? So we have to answer the question, is it at equilibrium? So we are looking for Q. Q is going to be equal to the pressure of H2 squared times the pressure of S2 divided by the pressure of H2S squared. So our Q is equal to the pressure of H2, which was 0.041 squared, times the pressure of the sulfur, which was 0.037, divided by the pressure of the hydrogen sulfide, which is 0.615. And when you key this into the calculator, you get a value of 1.01 times 10 to the minus 4. Now that you know where you're at in the equilibrium expression, you ask yourself, is K greater than, equal to, or less than Q? Q is less than K. So therefore, this reaction is not at equilibrium, and reaction will proceed towards the forward direction. Towards the products. Yes. I was supposed to square the bottom. Sorry. That's going to change everything. Thank you. 1.64 times 10 to the negative 4. It's still less than. Thank you. But yes, you were supposed to square the bottom. Thank you for catching that error. Questions about the process for Q? Basically, like I said, Q is calculated like K. It's just Q is the question mark of whether or not you're at equilibrium, whereas K means you are at equilibrium. The last section in chapter 15 that we're going to talk about is about finding equal concentrations at equilibrium. We will be doing a lot of this. Not only will I illustrate this with some general reactions today, but when we get to weak acid, weak base calculations, we do a lot of this. And so it is something you definitely need to be prepared to do. Now, another thing I will let you know is in some cases, you wind up with a quadratic equation that you must be prepared to solve. So one of the things, and I don't expect you to write out, I mean, you can write out the quadratic equation. You can solve the quadratic equation using, by plugging in B's and C's and all that into the equation. But on Blackboard, one of the things I did is create a video so that it shows you, if you don't already have it programmed, how to program the quadratic equation into at least a TI 84. And I recommend doing this because I will use the quadratic equation. I'm not going to sit here and solve it the hard way. So I expect you to do it that way. Also, when we get to KA, there is some assumptions you can make. Well, if you've got the quadratic equation, you don't have to make those assumptions because it's not very complicated. It's not much more complicated than doing the problem to begin. So I recommend just getting quadratic and being done. Now, if you have a calculator that's not a TI-84, you can come see me. If you can't find the instructions on how to program your calculator, we'll figure it out. Okay, so how are we going to go about finding concentrations at equilibrium? In order to be able to find the concentrations at equilibrium, the first thing you have to be provided is you have to be provided with the initial concentrations, and you have to be provided with the equilibrium constant. Once you have that, you're going to develop an ICE table, or sometimes it's referred to as a RICE table. And this table starts out with the reaction. That's where R comes from in RICE. The I comes from the initial concentrations. So you plug in your initial concentrations. The C comes from the change in concentration. The change in concentration is determined using stoichiometry. And the F is the final concentration, or excuse, I'm sorry, it should have been E. E is the concentration at equilibrium. Once you've developed your Rice table, you're going to develop your equilibrium expression or your law of mass action expression. You're then going to plug in these final concentrations into your law of mass action expression. You're going to do the algebra, and you're going to solve for X. And then once you know X, you can go back to these concentrations at equilibrium and plug that X into the formulas, and that will give you the concentration of each of your substances at equilibrium. So this is the process we're going to use. So a Rice table, again, reaction, initial concentrations, changing concentration, equilibrium concentration is where the E comes from in Rice. But basically, we're talking the final concentrations. It's just not as pretty of an acronym. I believe in doing examples, so that's what the remainder of today is examples. So for the reaction, where dinitrogen tetraoxide decomposes to form two nitrogen dioxides, the Kc for this at 500 Kelvin is 0.513. If the reaction vessel initially contains dinitrogen tetraoxide concentration of 0.05 molar at that 500 K, what are the equilibrium concentrations of the dinitrogen tetraoxide and the nitrogen dioxide? Okay, so the reaction is that the dinitrogen tetraoxide is going to decompose to form two nitrogen dioxides. For the initial concentrations, they have told us that the dinitrogen tetraoxide was 0.0500 molar. If this is the initial step in the reaction process, it means you haven't added the two chemicals together. You haven't added anything together. So you have none of your product initially. Now, as time progresses, the change in reaction, according to the stoichiometry, you're going to lose 1x of the dinitrogen tetraoxide, and you're going to make 2x of the nitrogen dioxide. So at equilibrium, the concentration of the dinitrogen tetraoxide will be 0.0500 minus x, and the nitrogen dioxide will be 2x. Now, we develop our equilibrium expression. The equilibrium expression is going to be that it is the nitrogen dioxide squared divided by dinitrogen tetraoxide. We're going to plug in our concentrations that we determined at equilibrium. So the nitrogen dioxide we said was 2x, and that is squared, divided by the dinitrogen tetraoxide, which we said was 0.0500 minus x. We also can plug in our equilibrium constant, which is 0.513 is equal to 2x squared over 0.0500 minus x. We're going to multiply through by the denominator on the right. And you get 0.02565 minus 0.513x is equal to 2x squared, which 2x squared is 4x squared. When you, as a reminder, if you have a square outside the parentheses, it means you have to square the things, both things inside the parentheses. So you have to square the number as well as the x. Now we're going to rearrange this equation to make it readily used in the quadratic equation. So your 4x squared is, I keep it positive. Okay. That's going to be plus 0.513x minus 0.02565. That is your A, your B, and your C in the quadratic expression. So my A is 4, my B is 0.513, and my C is negative 0.02565. And when you solve your quadratic equation, you come up with two possible values. You'll get 0.0385, and you'll get an x of negative 0.167. Only one will be valid. Only one of these will be valid. In this particular case, the negative 0.167 is not valid. Why is it not valid? Because here, if we plugged it in, you would have 2 times the negative 0.167. You cannot have a negative concentration. The lowest the concentration can go is 0. So we knew that this one could not be the answer because you cannot get a negative concentration. Second issue is you can't subtract a number that's bigger than the number you start with either. So logically, that could not be a correct value. Now we can plug in this real value into our equation over here, and we can get the concentrations. So at equilibrium, you have 0.0115 molar of your dinitrogen tetraoxide, and at equilibrium, you have 0.077 molar of your nitrogen dioxide. Questions? Folks, if you get a negative as the result of your quadratic equation, you can guarantee it's not it. Let's look at another example. Consider the reaction where carbon monoxide reacts with water to form carbon dioxide and hydrogen with a Kc of 102 at 500 Kelvin. If a reaction mixture initially contains 0.110 molar carbon monoxide and 0.110 molar water, what is the equilibrium concentration of each of the reactants of the products? So again, step one, develop your RICE table. R stands for the reaction. I is the initial concentration. They told you you have 0.110 molar of the carbon monoxide and 0.110 molar of the water. Because this is initial, it means the reaction has not begun. Therefore, you have 0 of the carbon dioxide and 0 of the hydrogen. As time progresses, this reaction is going to change. The change is that according to the balanced chemical equation, you're going to lose X amount of carbon monoxide. According to the balanced chemical equation, you're going to lose X amount of water. According to the balanced chemical equation, you're going to gain X amount of carbon dioxide. And according to the balanced chemical equation, you're going to gain X amount of hydrogen. So at equilibrium, you have 0.110 minus X of both reactants, X of and X of each of the products. We can now develop our equilibrium expression. It is the products over the reactants raised to their coefficients. Plugging in what we know, the Kc was 102. That is equal to X times X divided by 0.110 minus X times 0.110 minus X. I'm going to simplify this. 102 is equal to X squared. The denominator comes out to be that. I'm going to multiply the denominator through by 102. So it comes out as 1.2342 minus 22.44 X plus 102X squared is equal to X squared. When I rearrange this equation, I always rearrange it so that I get a positive X squared. That's just out of habit. So I'm going to keep everything on the left and move the X squared from the right to the left. And now I have my quadratic equation. My A is 101. My B is a negative 22.44. And my C is 1.2342. In this case, I get two values. I get one that says X can be 0.122 or 0.100. Only one of those is correct. here you have 0.110 and you try to subtract 0.122, you get a negative number. So it cannot be the 0.122. It has to be the 0.100. So therefore, at equilibrium, you have 0.01 of your carbon monoxide, 0.01 of your water. You have 0.100 of carbon dioxide and 0.100 of your hydrogen. Basically, I plugged this number in for X into the equilibrium concentrations to determine the concentration at equilibrium. Questions? I will not give you, I mean, technically you can have a polynomial where you have x cubed or x to the fourth. I'm not going to go there. I'm only going to stick to quadratics at worst. So you just have to be able to solve the quadratic equation at worst. Questions for me? If algebra is not your strong suit and equation manipulation is not your strong suit, you need to come see me or you need to go to SI and work with Elian. Because you will be doing a lot of these types of manipulations over the course of the next few weeks. That or you need to find a friend that is really good at algebra that can explain it. Questions for me? Then we're going to move on into chapter 16. I didn't think I would get here today, but I did post the PowerPoint this morning, so you do have access to it if you're one of those that's looking at the PowerPoint while discussing. Figure the more I can get done, the less we'll have to do next Monday. So I'm trying to get a jump start. Okay, so chapter 16 starts a discussion about acids and bases. We will actually discuss acids and bases in both chapter 16 and chapter 17. Chapter 16 introduces a lot of the concepts associated with acid bases, whereas chapter 17 brings in the titration of acids and bases and being able to figure out concentrations of the solutions at equilibrium or wherever they are in the titration. So we will be covering acids and bases for a good portion of the time. Now, you'll notice I included 8.7. No, I am not going to spend a lot of time going over 8.7. However, 8.7 refers you back to naming of acids and bases, which you need to be confident in, simply to make sure that if I'm describing something, you get it. So some general properties about acids. Acids tend to taste sour. Examples of acids that you would have tasted includes acetic acid, which is the primary component in vinegar. Citric acid, which is why oranges have that sour taste. You also probably have tasted malonic acid. Malonic acid is the reason that apples have a bit of a bite, especially Granny Smith apples. Granny Smith apples have more malonic acid than do Red Delicious apples, for example. Now, acids can dissolve many metals. Acids will turn blue litmus paper red, and they are used to neutralize bases. You actually have encountered this last piece back in College Chemistry 1 because you talked about acid-base neutralization reactions. Now, we're going to find out that those acid-base neutralization reactions were only a small fraction of the acid-base reactions that we can do. There are 3 definitions associated with acids that we are going to cover. The first one was covered in College Chemistry 1, and that was the Arrhenius definition. The Arrhenius definition is that an acid is a proton donor or an H+ donor. When you did the acid-base neutralization reactions, the acid donated the hydrogen to form the water. Now, the second definition is the Bronsted-Lowry definition, which again is a proton donor. So Arrhenius and Bronsted and Lowry all agreed as to what an acid was. They are proton donors, meaning they have to have an acidic hydrogen. The third definition, however, broadens the category of what can be considered an acid. Yes, a proton can be considered an acid, but so can other substances that can be electron pair acceptors. So in other words, we have to have an area that is electron poor that can accept a pair of electrons to be the Lewis definition. Folks, when we get to the Lewis definition at the end of this chapter, you need to make sure you understand this definition, especially if you're going to be taking organic chemistry. Because organic chemistry reactions are nothing but Lewis acid-base reactions. Now, going back to 8.7, I think I said, let's just talk about naming acids. The first thing is the inorganic acids. Inorganic acids can be divided into binary acids and oxyacids. Binary acids are acids of hydrogen and one other element. So hydrogen chloride, or HCl, excuse me, HBr, HI, HF, H2S, H3P, because those consist of only one type of, because those consist of hydrogen and only one type of element, Those are binary acids. All binary acids get named hydro. The base name of the second element, ic acid. So HCl is hydrochloric acid. HBr is hydrobromic acid. H2S is hydrosulfuric acid. H3P is hydrophosphoric acid. Again, those are your inorganic binary acids, and they get the hydroic acid. Your inorganic oxyacids. The oxyacids are acids of polyatomic ions that contain oxygen. But we're just going to talk about it as, we're going to broaden the category to be polyatomic ions. If your polyatomic ion, such as cyanide, is an IgE, then when cyanide makes an acid, it becomes hydrocyanic acid, meaning you replace the ending IgE with hydroic acid. If your polyatomic ion ends in ATE, then you replace the ATE essentially with ic acid. So sulfate becomes sulfuric acid. Phosphate becomes phosphoric acid. Nitrate becomes nitric acid. If your polyatomic ion ends in ITE, then the ITE becomes us acid. You replace the ending with OUS. So sulfite becomes sulfurous acid. Nitrite becomes nitrous acid. Now, with respect to whether it's the binary inorganic acids or whether it is the oxyacids, the number of hydrogens are going to be equivalent to whatever the charge on the anion is. Now, when you're looking at a acid, especially the inorganic acids, when you're looking at these, the formula will start with the acidic hydrogen. So HCl, that H at the very beginning of that formula is your acidic hydrogen. H2SO4, those two hydrogens at the beginning of the formula are your acidic hydrogens. HCN, the hydrogen at the beginning of the formula is your acidic hydrogen. Now, I specifically focused on inorganic acids on this slide, but you can also have organic acids. Organic acids, the organic acids are called carboxylic acids, primarily. However, it doesn't have to be a carboxylic acid, but that is the most common form of is the carboxylic acid. You have experience with a carboxylic acid when you make acetic acid. The acidic hydrogen is going to be the hydrogen that's attached to the COOH group. That is your acidic hydrogen. If you look at citric acid, it has 3 acidic hydrogens. All 3 of them are attached to a carboxylic acid functional group. as you saw yesterday with bromocresol green in the post lab, an alcohol can be considered an acid. Now, and as in college chemistry, when you see an OH group, you typically go to, oh, that's hydroxide. That is true if we're dealing with inorganic compounds. If you're dealing with inorganic compounds and you see a high OH, then we're talking about hydroxide. For the most part, with what we're talking about with these inorganic compounds is going to be something like a metal hydroxide. But for organic compounds, when you see an OH group in an organic compound, it's called an alcohol. An example that many people have some experience with or know about is ethanol, whether it's through gas tanks or whether it's through drinking alcohol. It's ethanol. One thing, and in this particular case, the acidic hydrogen is the hydrogen attached to the O. So I want you to note a couple of things about these organic acids that I'm bringing up. One is that acidic hydrogen is attached to an oxygen. You'll recall oxygen is the next to most electronegative atom on the entire periodic table. Meaning that oxygen loves its electrons. And that oxygen is going to steal the electrons away from the hydrogen, and that's where the H plus comes from, is because when these break apart, those electrons that are in the bond go to the oxygen. The other thing I want you to note is when we deal with organic compounds, and this is going to be something you're going to see, you will notice that I did not finish the Lewis structure. A lot of times when you deal with organic compounds, you are supposed to already know that oxygen has to have 8 electrons. Right now, it only has 4. Therefore, it has 2 lone pairs. You're supposed to know that without being able to see those. This oxygen up here, again, you're supposed to know it has to have an octet. So since it only has 4, that means it also has 4 in lone pairs. You're just supposed to know that. So we don't tend to write out every single dot when we're dealing with the organics. We don't do it that much anymore, period. You're supposed to know this stuff. I think that's a good place to stop. We'll pick up with bases, and then we'll get into acid, a little bit more about the Bronsted-Lowry acid-base definition on Thursday.